So the plan for today is to cover a little bit which I didn't finish from chapter 5, and then to start chapter 6. So let's recall what we were doing. So I won't talk about topology, just usual complex story. So using some theorems about covering, we constructed argument functions. So there are two contexts. So one is when you inside C without 0 simply connected, and then we define kind of arguments depending on U. So the function from U to R. Notice that in this case it was just a function. So there were many of them, but we didn't use any parameterization. There was another context when we had gamma a path to, and then we defined argument along the path, also a function. So both not unique, both non-unique, but always for two different choices, the difference being a constant function, and this constant function is a multiple of 2 pi for some n in z. So they are of course continuous functions, and using these argument functions we considered already canonically defined variation of argument along the path. Which was simply the difference of values of argument function at the ends of the path. And this does not depend on a choice of the argument function, because all the ambiguity is cancelled out by the difference, and in particular for loops, for paths where the endpoints coincide. So we define also define the winding number. For loops. So winding around 0 is simply still variation of arguments. Along gamma. Okay. So also for U in C without 0 simply connected, considered a holomorphic section So we call it a logarithm depending on u. Yeah, and we proved that any such is a primitive for 1 over z. In U. In particular, we using this, we obtain a series for logarithm. So there's a standard choice of logarithm among these. So standard choice of cut and standard choice of pre-image, so that the inverse function would be defined. And just we calculated all derivatives of this. So found. And then the series was given by the usual formula. Very good. So using exponential functions and logarithm functions, we can also talk about here. So using Lu and x, we can define functions z to the alpha for alpha any complex number. And the rule is that if we chose already logarithm, then our choice of this will be expressed by the obvious formula. Wherever, so u simply connected in z with in c without 0, and Lu the choice of logarithm. Then, so notice that if we take z to the alpha and divide it by z, then this will be z to the alpha divided by, just by definition of logarithm. So this will be x of minus Lu of z, x of alpha Lu of z. This is x of alpha minus 1 Lu of z. And we agreed that this is just z to the power alpha minus 1. So see, the notation matches. So in principle, this is some random strange expression and depends on a priori on the choice of logarithm. If we divide it by z, then we'll get a similar expression. So it's concise. So let's differentiate z to the alpha. So obviously, as a composition of holomorphic functions, z to the alpha is holomorphic in U. And let's differentiate. So this will be and then we use the chain rule to get that this is but we already mentioned that the derivative of any choice of logarithm is 1 over z. So then this is and then by the calculation I made above, this is so in the same way, if we do it many times, so iterate. If we take z to the alpha and then differentiate it, say n times, so then this will be alpha times alpha minus 1 alpha minus n plus 1 times z to alpha minus n. So, of course, this coefficient might be 0. So, if alpha equals one of them, or one of these, I mean, if alpha equals to 1, this will be 0. If alpha equals to 2, the next one will be 0. So, in integer exponents, we'll get expected behavior that, say, second derivative of z squared is 0 and so on. So this function actually coincides with the function where we know a priori integer values of alpha. Good. So having this in mind, we can just write in u being just yeah, so I need to decide. So let's say that it's like this. Okay, so it's a circle around one of this is k of 1 1. We can write Taylor extension. Or 1 plus z to the alpha. So notice that my choice of this disk makes it simply connected and totally inside C without 0. It's an open disk, so the point 0 is not there. Yeah. So then I should start differentiating, and I'll get that this is sum n greater or equal to 0. Alpha choose n, z to the power n, where alpha choose n is almost on the blackboard. And again, it coincides with the expression which we know for alpha integer. So if you think about it, this indeed is a ratio of, so for alpha, so for alpha integer, alpha n, alpha choose n, is indeed alpha factorial divided by n factorial alpha minus n factorial. But when alpha is not integer, infinitely many of these are non-zero, so we actually get series which we know. Good. So this is the last thing I wanted to talk about from chapter 5. And let's start talking about next chapter, which is zeros and isolated singularities. Of homomorphic. So let's start from zeros. So with a theorem, let G be a domain. Let's see. So just like the previous topic was rather geometric by nature, this topic is rather analytic by nature. So suppose we have a domain and a function which is holomorphic in the domain. And suppose that f is not 0 as a function. So it's not constantly 0. And at some point a in G, f of a is 0. Then there exists unique number n, and G, which is holomorphic function in G, with G of a not equal to 0, such that f is z minus a to the n times G. So the meaning of this is clear. In a way, in the neighborhood of this point, we want our function to behave as a polynomial z minus a to the n. So anything related to the fact that the function takes 0 should go to the first factor, and the second factor which should be just an invertible function. Okay, so let's prove this. So we have this G, and we have A. Let's choose a radius of maximal value such that the disk of radius rho is inside G. Yeah. So certainly remark what we want to do. We want to measure n in the expression via Taylor series of f at a. So so let's write these expressions. So we want to see the relation of f of a with derivatives with some other f of z node, where z node is another point in this K A row. So so we have this big disk, radius rho, around K, and we have Z node. So what we start doing, we start expanding F by power series in small disks and passing the information from A to Z node. So to do this, we connect Z node and A by a path. So gamma is a path in a row connecting A and Z node, and do what we usually do. So we cover this path by finitely many disks in such a way that the first disk is around A, and the last is around Z node, and the center of the next disk is inside the previous one. So we have these disks, have finitely many disks. Okay, let's say gamma of Ti Ri. So with gamma of 0, certainly of T0, so 0, gamma of T0 equal A, and gamma of Tn is gamma is the last one, so is Z node. In such a way that so power series of F centered at gamma of Ti converge. So let's see what we get from this. In the first disk, so here, as you notice, we used that the disk is path connected. Okay, so anyways, in the first disk, we have the expansion of F. So if all these coefficients vanish, then it follows that same is true for f of z in the first disk. We know that. So then all derivatives at gamma of T1 also vanish. So then f is totally 0 in the second disk. And so on. So in the end we get f is 0 at z node. So we proved that if all derivatives vanish at a, then the function completely vanishes. So not all of them are 0, so I can write so not all so find the first which is not. And this will be our n. So we'll write that f of z. I'm just rewriting Taylor series. I'm taking this power out of the bracket. So we can write, so we can define the function. G of z like this. So whenever I have the convergence, I can define it just by sum. So first of all, outside of the point A, I can just divide. So when I'm in Z in G without A, I can simply define the sum. I mean, I can simply define G of Z as f of Z divided by Z minus A to the n. And in the disk, I can define G of Z by this formula. So this works for. So this is in the convergence disk. I'll say raw. So it's a well-defined function, and on the I mean, these two expressions match on the intersection. On the intersection, it's k prime a rho, and these expressions match. These expressions agree on k prime a rho. So yeah, obviously, by the definition, now we have it everywhere. So now, everywhere in G, f of z is z minus a to the n G of z. It's true outside of the point A, and it's true in the disk of convergence. So it's true everywhere. Also, G of A is not zero. So G of A will be f A and factorial. So I proved existence of such presentation. Now about uniqueness, it's even better. So if we have z minus a and 1 g1 of z equals z minus a and 2 g2 of z, and let's say n1 is greater than n2, greater or equal to, doesn't matter. So then we can divide, and then we'll see that and of course g1 of a is not 0 and g2 of a is not 0. We'll come to contradiction very fast, because then z minus a to n1 minus n2, g1 of z will be g2 of z. And now we evaluate at a, left hand side of a is 0 unless n1 equals n2. So n1 must be equal to n2, because right hand side is not 0. So it follows from this that we get g1 of z equals g2 of z, and n1 equals n2. Okay, so this was almost tautological. So I proved existence and uniqueness of this presentation, and now I'll use it. So now we'll prove the following principle. So we mark. We will prove every 0 of f in is isolated. So, in other words, the following situation is impossible. So there's no holomorphic function which takes 0, say, here, or whatever. So impossible. Impossible sets of zeros. Okay. Let's see. So theorem. Suppose we have a function which is holomorphic inside the domain G, and it's not completely 0 as a function. And A is 0 of f, so f of A is 0. Then there exists a disk, punctured disk, inside G, around this point, where this function does not finish. Okay. So is very simple. So use the previous theorem. So decompose f of z. So our L, g of z, where g of a is not 0. So first of all, the only 0 of this function is a. So for any disk, I punched this a r, z minus a to the n has no zeros there. It's a function. Also, g is continuous. Let's say that g of a is, I don't know, capital A, which is not 0. We can find some disk. For which absolute value of g of z minus g of a is less, say, than a over 2. It's a non-zero number, so then we'll get is never 0 in the disk. So then the product is never 0 in the intersection, which is k prime a r, because first factor is not 0 just outside of a, and second factor is not 0 inside this disk. So then the product is not 0. Good. So we proved the theorem. Now, in a way, we are getting a corollary which is approximation result. So you should compare it with the following. So this is remark. Suppose we have polynomials f of z and g of z. Just polynomials, right? And suppose that degrees are less or equal to n. Then, by standard algebraic methods, we know that if there exist n plus 1 points, a naught, a n, where they coincide, it follows that f equals to g. And the point is that you can write linear equations on coefficients. So method of proof, method, values at n plus 1 points, different points, give you all coefficients. Of a polynomial. So, we're comparing this with the following. So for holomorphic, I mean, these are, of course, typical examples of holomorphic functions. But there are more general holomorphic functions, like sine, for example, which can have infinitely many zeros. So here we're using that polynomial function as finitely many zeros. So theorem, which is a generalization of this. So suppose we have two holomorphic functions. Suppose there exists A in G, a subset on which f of A equals G of A in A, and it is not discrete. Then f equals to G everywhere in G. And the proof is clear. It follows from the previous one. So, proof. Let's take H, which is f minus G. Then, for every A in A is a zero of H. So the point, the fact that A is non-discrete means that, so A non-discrete means that there exists an accumulation point of A. So there's a sequence of points, A1, AN, so on, such that lim AN is A0, some particular point. Now, notice that for every I, f of AI equals G of AI. In other words, H of AI is 0, and H is continuous, of course. Then H of A0 is 0. So A0 is one of the zeros of this function. So if f is not equal to G as a function, H of A0 is 0, but H as a function is not 0. Use the previous theorem. There exists an open, there exists a punched disk K prime A0, let's say R0, where H of Z is not 0 for every Z in this one. But this contradicts the fact that it's accumulation point, because in this neighborhood there should be other points from A. So, but there exists N, A, N is in this K prime A0, R0. Contradiction. Yeah. So when I write this, of course I mean that all points are different, because otherwise it's not interesting. I'm actually counting, it's not a sequence, it's a collection of points. So let's make a break. We'll slowly go further through